Okay, welcome to another Orbiter 2010 video. And in this video, we are once again going to learn how to use IMFD. In the previous videos, we learned how to go from the Earth to the Moon. So now it's time to learn how to go the other way around, how to go from the Moon to the Earth. Now this scenario is one of the defaults that comes with Orbiter 2010. It's located in the Delta Glider folder. This is the Delta Glider landed at Brighton Beach. So if you load up this scenario, you should be able to follow along quite easily. I have Dimitri with me again to help us learn how to do this because I am the IMFD newbie. I don't know much about it, so I have to have help for all these steps. So Dimitri, what do we need to do to use IMFD to get back to Earth?
Okay, hi everyone. Basically, I'm going to tell you the steps that we are going to do. We are going to use the Planet Approach program, so we have a trajectory to Earth. And once we have that, we're going to use the Surface Launch program in order to get into the correct orbit around the Moon, and then the Orbit Eject program to perform the actual burn that is going to get us to Earth. So we can start by bringing up IMFD on the left.
Okay, let's do that. Let's bring up IMFD over here. And we have the default screen here, so we need to press the MNU button. And we were bringing
and
up
we select the course program,
course.
and now we select the Planet Approach.
Okay, so we'll go down to next till this is highlighted, then press the set button. That'll bring up the Planet Approach. This is pretty complicated looking stuff, so hopefully we can get a good explanation here of what we need to do.
Okay, the first thing we need to set up is a trajectory from the Moon to Earth. Now, the Moon is orbiting the Earth, so the reference planet over here, the central planet in our view, should be the Earth, and we select that by selecting reference and typing Earth.
Okay, could you maybe just expand on that a little bit? Why are we referencing the Earth if we're on the Moon? Is it just because the Moon's in orbit around the Earth?
Well, it's the same as TransX, where you have a major body in the center and a minor body orbiting around it. And this is exactly what we're setting up over here. Now you can see, because we have the source, the ship right now, and not the Moon, it tells us that we have an invalid source. So we have to change that, and we want the Earth at the center and the Moon as the source.
Okay.
As the source of the trajectory, in a sense.
So when we selected the Earth as the reference, we were setting the major body, basically. And now we're setting the Moon as the source. And now we have data that makes sense.
The Earth is right here at the center, and this blue and green line is the orbit of the Moon. What we want to set up now is our approach to Earth. First thing that we want to set up is the equatorial inclination that we want to arrive at. Basically, here we set up a number, a rounded number, relative to the latitude of our base. If we want to arrive at a base at 28 degrees latitude, it would be good to set up at least that much equatorial inclination. Otherwise, we're not going to have enough inclination to arrive at our base.
Okay, and just as a point of reference, if you don't know the latitude of the base, what you can do, bring up map MFD on the other side, reference the Earth, and then target the base you want. Let's use Cape Canaveral as our example. So if we target Cape Canaveral over here, then we have the latitude and longitude down here. And of course, we want the latitude, which is 28.52 for Cape Canaveral. But you're saying that we wouldn't actually set the EQI to 28.52, rather we would maybe go a couple degrees higher?
Yeah, go to the next round numbers, something like 29 or even 30 degrees would be okay.
Okay, so we'll use the previous next and go down to the EQI and then hit set, and we'll just round it up to 30 degrees. Okay, so then
the next thing you set is the periapsis altitude.
Okay, so after setting the EQI, then we go down one, and the PEA is currently, of course, way out in space. And do we want like 65 kilometers for atmospheric
No,
reentry?
because right now the planet approach program is not very accurate from where we're standing right now. So you can set it around 500 kilometers, and it's going to give you to get you to close to Earth. Anyway, we're going to make a course correction when we are inside Earth's sphere of influence.
Just out of curiosity, so IMFD, like all parts aren't equal, so it's just the map program that has that highly accurate model, whereas like
Yes,
these other programs don't quite have the same accuracy. Is that how that works?
exactly.
Okay.
Exactly. This program is not that accurate, especially when you are already landed. If we were already on a trajectory to Earth, it would be slightly more accurate, the prediction that you get from here. But since we are right now, we are landed, and we have to go uh, first into orbit and then eject to Earth, and after that, this is where that program takes over. And don't forget that right now we're seeing the source as the moon and not
Mm-hmm.
the ship. So basically, what this says right now, if you wanted to move the moon and get it at 30 degrees equatorial inclination and 500 kilometers per Epes altitude, you would need this much delta V. Of course, you would need an insane thrust, but the delta V is the same.
That would be an impressive trick.
Yeah.
Okay, so we now know that we have a course set up to get back to the moon, but we're still landed here on the moon. So obviously we can't just BVAB to auto burn. We've got to do something else. What else do we have to do?
Yeah. So we open up another interplanetary MFD on the right side, and we connect it to this one.
Okay, so I'll bring up Transex or interplanetary on the right side, and to connect them, we just press MNU, and then we press the page button, and we need to put in the ID for the left side, and the left side ID is always 0. So I put
Always
0.
left 0, right 1, always.
Okay, so these are now connected.
Okay, and now we're going to use the surface launch program.
Okay, makes sense. We're on the surface. We need to get off the surface, so surface launch.
Okay, and you can see it has already connected to the course program. This is what we're using on the left side. And right now, the op mode, where we share the data, is on the course program, which is what we want. So now, basically, all we have to do is take off at this heading. The values that we're interested in is the heading, what we have to follow to get to the correct orbit. This shows us the periapsis and the apoapsis of our orbit. And this number over here, the eject inclination, is how many degrees we are off plane relative to this trajectory, basically.
Okay, so the surface launch program is telling us what we need to do to get up into orbit so that we can use this course. And the reason that we're not having to configure anything on this side is because this side is shared with this side. So this is using the course program to calculate all this information for us. I'm guessing if we didn't share the side, then when we brought up the surface launch, then we'd probably have a bunch of erroneous data over here that didn't mean anything.
Actually, the surface launch program, I think it always has to be connected to something. You can see over here, sorry. You can see over here from the choices that you have, you either connect it to the base approach program, to a slingshot, or to higher orbit, of course, that's from the orbit eject program. Lower orbit, and then back again, I think. There are lots of different options, but in this case, we have a course selected on the course program on the left. So we want to use the course program, we want to share it with the course program on the right. And as you saw, it always has to be shared with something. Otherwise, it doesn't make it asks you with what do I need to connect in order to launch.
Okay, so basically if you bring up the interplanetary on the right side and you don't have this data, then you're not shared or you're not connected to the course program, and that's what you have to do in order to get this data. And this data is obviously critical because you need to know that when you lift up off the moon, you don't just want to fly out at 70 degrees, which is the direction we're facing. We don't want to fly out at 90 because then our inclination will be way off. So we need to know what heading to go to. And we get that information right here, about 57.559, about 57 and a half. Okay, so is that all that we need to do here on the ground? Are we ready to get into orbit?
Yes, we're at get in orbit right now. Another thing, this is not very crucial, but here we have set up a trajectory, and we're actually going to fly this plan, not exactly right now in 0 seconds, but when we get into orbit and arrive at the point where we need to make the burn. For a launch from Brighton Beach, that usually happens at around 5,000 seconds, 5 to 6,000 seconds uh, after the launch. So just a very minor correction, not that it really matters, because after all, we're going to make a course correction when we are inside the Earth's sphere of influence. But it's a good practice to actually use this parameter over here and set the time to ejection close to when you are actually going to make the burn.
Right. Okay, so basically, let me explain in my own words what we're talking about here is when we get up off the moon and get up to orbital velocity, we're not going to instantly go back to the Earth. We need time to get around to the correct eject point. And that eject point is going to be maybe about 5,000 seconds. That's just a ballpark figure. But by setting that here, so we'll set it for 5,000, that's going to have some impact, on your heading. Is that about right?
Exactly, and you can see already that it changed over here. We were at 55.5, I think, and now we're about 1 degree difference.
Yeah. Okay, so that will have some impact again. If you didn't do that, then you might have maybe a little bit larger of a mid-course correction or something like that. But it's, as Dimitris said, it's good practice to go ahead and set that as well. Okay, so then is that everything?
Yeah, we're ready to go. There is also one other parameter over here, the altitude of the parking orbit, but it makes no difference whatever you set it, because you can fly out to whatever altitude you want at this at the surface launch program. So even if you set this at 20 kilometers, for instance, it doesn't really matter. You will get to whatever orbital altitude you want.
That's not going to affect your heading or anything like that.
And exactly, it's not going to affect your heading.
Okay, well, let's change the projection then to self. That way, as we're getting up into orbit, this orbital line here, it'll look more like it does in orbit MFD. Whereas if you have it set to the default of ecliptic, then the orbit line's going to be all kind of cockeyed as you're getting up off the ground, and it could be confusing. So you don't necessarily need to bring up orbit MFD because you have your PEA and APA here that you can follow. Okay, so let's do that. Let's 0 to get some hover thrust. Bring up the landing gear. I guess I could have used the scenario editor to get rid of some fuel, but I forgot about it. And we need a heading of about 57 degrees. Not quite, about right there. Full power on the main. Eliminate the hover. And pitch up just a little bit. We don't want to pitch up too much. And we can follow the EIN here. This lets us know if we need to yaw the vessel left or right. We want to keep the EIN as close to 0 as possible.
You saw already that as soon as you got less than 1 degree of relative inclination, it turned green, which means that you would be able to fly this a trajectory even as far as 1 degree off plane. But it would cost slightly more in delta V. But it's always good practice to get your eject inclination as close to 0 as possible when you're going into orbit.
Yeah. Speaking of load is close to 0, let me do a bit of a yaw adjustment here to bring that down. And now we just watch the orbital line here as it starts to grow. And when we get up to a periapsis, or rather we get up to apoapsis of about 20, maybe 30 kilometers, then we'll kill the engines. Let me yaw a bit to the left. And we'll be up to orbital velocity here in just a moment. And I really got to concentrate in these last few seconds or I'll do something really stupid. And bring the APA up. And right there is about 20 kilometers. Okay, so
Okay, now we are done with the launch program, and the next thing that we want to use is the orbit eject program. First, we want to circularize the orbit, but uh, always check when you need to make the eject burn before you circularize the orbit, because right now you're going to have to reach apoapsis, which is about here, I think, and circularize the orbit. There is a chance that you may have to make the eject burn over here. So there is no point in circularizing the orbit. You can go ahead and right away make the eject burn. So first we're going to check when we need to make the orbit eject burn, and then we will see if we need to circularize the orbit or not.
okay, so if we reach the eject point before we reach apoapsis, then obviously there's no point in circularizing the orbit first because we would actually miss the eject point and would have to go all the way back around.
Exactly.
Okay, so we're done with surface launch, so I'm guessing we can use the left side to bring up orbit eject, or rather the
Yes.
right side. So bring
The right side.
yeah. Okay. And what are we looking
you
at
want-
here?
Here again, you want to select which program you're sharing from the left. Right now, you want to see here that you're sharing the course program, so you want to change that with plus or minus until you see the course program.
Okay, so right now it's setting on higher orbit. That's not what we want, so we'll go plus, and now we're at course. So we're now sharing the correct program.
Okay, and now you can change the projection to see
Yeah, let's do that.
it a little bit better. And right now we're here, and we're going counterclockwise. We have a prograde a direction. Here is the apoapsis, where we're going to circularize, and the burn is 5,800 seconds away. Over here. So first we're going to circularize, and then we're going to make the burn.
Okay, so in this case, we're definitely going to reach apoapsis long before we need to do the eject. So the priority here is going to be to circularize the orbit. Now, I do have a question. Are we at all out of plane from the original plan? Did we arrive in orbit with a 0.000 inclination, or were we a bit off?
You can say it over here.
Okay, so we're out by 0.2. Do we not even need to concern ourselves with that at all, or can we fix it?
No, not.
Okay.
This is the delta V. You need to fix it. 0.651.
Okay,
And
so
the
it's
node,
nothing.
yeah.
Okay, now when we get over here to circularize the orbit, can we use the orbit IMFD orbit circularization, or will it forget this data if we switch out of this program?
No, we will not lose anything. You can go ahead. You can switch to orbit MFD or something, so you can see how far away you are from apoapsis on one side, and then you can use the orbital program and the circularization program to circularize the orbit.
Okay, so we'll bring orbit MFD up over here so we can see where apoapsis is at. Then over here we'll bring up the orbital program, and circularization is the default. So basically we're just going to go all the way to apoapsis because BT is less than 1. So basically as soon as we're at apoapsis, maybe a couple seconds sooner to give it time to orient. Okay, so warping time 4, getting over to apoapsis. Getting pretty close to that point. And we're basically backwards, so let me hit...
You can do it with linear translation with a 9.
Yeah.
Translation. Rotation. translation.
Just doing a bit of linear translation to bring up the PEA instead of using the orbit circularization program. Time to apoapsis is counting down. And if we had the retro doors open, then we could have used those as well, but okay, the orbit is okay, there we're circularized.
Okay, now you can go back to the orbit eject program, and even this far away from it, you can still press the burn vector and auto burn and time warp to the burn. The IMFD is going to take care of the rest.
Okay, very cool. So from this point, we just page over to the other page of variables, and this should be familiar by now because we did this going out to the moon. You just press the BV button, then auto burn, and even though we're 3,500 seconds away, IMFD will handle everything for us, so we can actually time warp forward all the way out to like 1,000 at this point. And when it gets down closer to the time to burn, IMFD will automatically reduce to 100, and then when it gets down to a couple hundred seconds, it'll automatically reduce to 10x, so you don't have to worry about overshooting and missing the burn. So let's go ahead and do that. Let's go out to 1,000. And there, reduced to 100. And now down to 10. Now it orients the vessel and will complete the burn automatically. And if we watch Orbit MFD on the left, we'll actually get to see the expansion of the orbit. And now that that's done, kind of jokingly, I'll ask you the same question I asked when we went to the moon. So now we can just warp time forward at 10,000 and here the vessel will land itself at Cape Canaveral and everything, right?
Yeah, under a hangar, whatever you want. No, not exactly. Of course, we're going to have to make a correction and align ourselves with the base that we want to arrive and set our periapsis altitude, because when this trajectory that we're following right now is a rough trajectory that will get us close to Earth, about at the inclination that we want to arrive. From there on, we're going to have to make a correction to be more accurate about our arrival.
Okay, so
But
for
for now,
now,
all we have to do is to time warp until we are inside Earth's sphere of influence.
yeah. So let's reference Earth on Orbit MFD just so we can keep track of the gravitational influence, and let's time warp out.
Rotation.
And we know that we're going to be in the influence of Earth because the orbit HUD will update. It'll go from orbit Moon to orbit Sun, and then from orbit Sun to orbit Earth. And we can go a little faster. It's got to 10,000. And we're now between the
You can
two.
see when we left the lunar sphere of influence,
Bon voyage.
the orbit eject part of the plan is done.
Okay, so we're completely done with that program. And we're almost, there we are, we're now in the influence of Earth. So I'm assuming now we want to do some kind of mid-course correction.
Yes, now we're going to use the base approach program in order to align ourselves with the base that we want to land and to set our periapsis altitude.
Okay, so we'll press
So we
MNU
go
to go
to-
back, and then base approach.
Yes.
Okay,
Now you target the base that you want to land.
target. And can we adjust the projection here? I hate seeing that kind of projection. It's
Yes.
weird. All right. The self probably.
Okay. You can also zoom out a little bit to see the spacecraft where it is right now. It's right here on this green line.
Okay, so we can press PG to get to these variables and then zoom out. And then we can see where we're at here. Okay.
And now you need to set your periapsis altitude.
Okay, so page back over to these variables and go through next until we get down to altitude. And then we want about 65 kilometers.
65, 60, it's not that we're going that fast right now. With the Delta glider, I usually set it to 60, but
Okay, we'll go 60K.
whatever you prefer. Either we were not going to finish the re-entry and land, we're just going to get to the point where we are aligned with the base and inside the atmosphere. Now, we need to select what kind of approach we want to make. And the easiest way to select this is to use the orbit insert program right here.
So instead of approach for reentry, we go to approach for, and then we hit the plus or minus button to get orbit insert.
Yes, and it's telling you right now that you are going to need to have 110 meter per second correction in order to arrive at Earth, and you will be aligned with the base and have this periapsis altitude. But there is one problem when you use this kind of setting. You have no control of where, how close to the base that you are going to land you will arrive.
Okay.
For example, you may arrive slightly past Cape Canaveral and have to go all the way around the Earth to get back to your base. But since we're showing this video for the simplest way to do this, this is good enough for now. We're going to do another video where we're going to have a much more accurate flight from the moon to Earth. Now, there is one thing that you can do to actually improve your distance to the base, and that is to select the antipode on Earth. What that means is to select the coordinates that are exactly on the other side of the Earth, as if you dug a tunnel and you ended up on the other side.
Mm-hmm.
And to do that, you go to the latitude and you select the same latitude, but on the other side of the equator. So that's going to be minus 28.521.
Okay,
So let's do that.
Put
It's
that
going
in.
to slightly adjust our re-entry, let's say the coordinate, where we arrive, how close we arrive at the base. So we have that, and now we need to select the other side of the Earth. Basically, we want to add 180 to this number. When you have a longitude, when you say west, it's like saying minus 80.675. And you want to add to that 180.
So if I'm understanding, then it would be 100.675 east.
Not exactly. Bring up a calculator.
Okay. Okay, we got a calculator up.
Okay. This is the. Can you enter a minus 8?
Yep.
Oh, no, it's the same thing. 180 minus 8.675.
180 minus 80.675.
Yes.
Okay.
And you can see it's 99,327 on the east side this time, but it's you will enter a positive number now. So you go to the longitude and press and enter that number.
Okay. And it was 99.325. Okay, so is my understanding, we're trying to tell this base approach program that we want to arrive on the opposite side of the Earth, is that correct?
Yes.
Okay.
Yes. So it's not going to arrive exactly at the other side of the Earth, but we're going to be much closer to the base, because if we used the coordinates of the base, we may end up a few hundred kilometers past the base and have to do a complete orbit to get back to it. But this way, at least we're making sure that we're going to have a distance less than half an orbit.
Okay, that makes sense.
To
So
arrive
at
at
the
the
very
base.
least, you're going to be far enough away from the base that you can land basically within a half orbit, or you're not going to have to go all the way around.
Yes, half an orbit, or when you use this method, this is called the antipode, and you saw how you set it up. For the latitude, whatever was the latitude, you go on the other side of the equator, and on the longitude, you add 180 degrees.
Okay.
And you go on the other side of the Earth. And with that, you ensure that you're going to arrive at a point where you would have less than either half an orbit or less than that to get to your base. Otherwise, you may end up with a periapsis point a few kilometers past the base that you wanted to land, and you have to go a full orbit around.
And I noticed in this case it had the happy coincidence of giving us a lower delta V as well, because we were at 100 and something, now we're down to 63.
And also, whenever you have this kind of maneuver at the beginning and when you enter the sphere of influence, always check if you push the maneuver a little bit further into the future to see if that actually gives you less delta V or more.
Okay, so basically we want to check to see if it's best to do the maneuver now, or it might be better to wait another 10 or 20 or 30,000 seconds, or even a day or a half day. So let's go to TEJ, because that's basically saying when the maneuver is going to happen. And then we'll do an adjustment out to 10 and just add in some time and see if it goes down or up or what it does. See, it's not really having much impact, but as we go much farther forward, it's just continuing to increase.
Well, if you zoom in a little bit, you can see that the node for this maneuver was actually out here. You can see this
Can we zoom
a blue line over here. Yeah, you can zoom a little bit.
zoom in closer to Earth? Okay.
So basically it was, yeah, we can say it very clearly, but it was this blue line. So if we were exactly at that node over there, right here where it extends all the way out of almost close to the moon, we would probably need less delta V than that. But even this is not that much.
Yeah. Okay, so in this case, we're not saving any delta V by waiting, so we'll go ahead and go back to the other page, set the time to 0, and basically just plan on doing that maneuver now.
Again, you hit the page button and the burn vector and the auto burn.
Okay, so page over to get access to these variables, BV and auto burn. Orients the vessel. And 63 meters a second later, we have our PEA. Of course, the orbit IMFD PEA isn't reliable at all at this point. Okay, so that's that. Now,
Turned out pretty close. It turned out. Now, what I do here is wait until I am about 1 hour before periapsis and repeat this step.
okay, in 1 hour that would be how many PET?
3060 seconds.
Okay, so then the next step's
And-
to warp time forward to that point.
And I also look at the total delta V. If that goes above 10 meters per second, whatever comes first, either this to 10 meters per second or the PET to 3600.
Okay, same as kind of getting out to the moon, then whichever comes first. Okay, let's warp time forward, and we'll keep an eye on both of these, and make sure that we stop the time warp on time. That's kind of jumping all over the place. I notice as I go above 1,000 in orbiter, I have issues. I'm not sure why anymore. It seems like something that just started happening. But I get a lot of crashes if I go above 1,000.
Yeah, sometimes you install a few things even unrelated to orbiter and then they have an effect.
Yeah, I really hate to think that I need to scrap my orbiter installation and start over, because my orbiter install is, quite built up at this point.
I have several orbiter installations. I think I'm up to 6 or 7 right now, but most of them I keep because I have some flights or some textures or some base that I made, and I want to keep it, and I remember that I have it there. But otherwise, I also use a single orbiter installation for most of the stuff, and if something happens to it, then I don't even want to think about reinstalling the whole thing.
Yeah. What you'll notice here, what I'm talking about, like, okay, right now we're at real time and it says the total delta V is 6.83. But as I go to 10 or 100, you can see it starts increasing. And if I go to 1,000, it jumps way out. And then, but
No,
it's,
okay, that's just what I do in order to make it make the flight a little bit more fuel efficient. There's nothing wrong with letting it go all the way to 1 hour before periapsis and then making a slightly bigger correction.
okay. So we're just not even going to worry about the DV jumping all over the
Yeah.
place then, because it's too much. All right, so watching time. And we're getting down now. We're only 6,000 seconds out. 4,000, and we're going to go to 36. So right about here. Okay, and yeah, it did increase our delta V quite a bit, but well, we'll have that. So here, I'm assuming, since we're already on the BV page, we probably just have to hit AB.
Yes.
Okay, let's do that.
Again, and you will see that we'll go to periapsis exactly 60 kilometers. And we can also take a look at a map MFD to see where we arrive.
Yeah, I'm kind of wanting to look at that here before we start the burn. So let me go to orbit plane. And I believe we have, yeah, we've already got the base targeted. So as I do the burn, we'll see what happens to our orbit line here. And this is only 26 meters a second, so it certainly isn't that much. Okay, so it actually still kind of looks like we're missing Cape Canaveral, so I'm guessing...
Well, we are 1 hour before periapsis, and the Earth is rotating at 0.25 degrees per minute. So 60 minutes times 0.25, that's about 15 degrees. The Cape will rotate about 15 degrees from where it is right now.
Okay, which is about half of one of these squares, so by the time the rotation's done, it should be about right there. And we're only 7,000 kilometers from there. Let's look at orbit MFD. And yeah, the PEA is right there at about 60. All right, so I guess we would just warp time forward to get down to the atmosphere at this point.
Yeah, let's see how close we got. We don't have to actually land.
Right. Yeah, that'd take another hour. So let's warp time forward till we get our altitude down, and let me
Translation. Rotation.
rotate forward just so I know where we're going.
Translation. Rotation.
Yeah, in this case, it looks like we're actually going to arrive at periapsis almost over top of the base, so we'll have to definitely go all the way around.
Yeah, the only problem is that we're going to have to go all the way around.
Yeah.
So this is the problem with this approach. I was hoping that that the antipode would help, but in this case it did exactly the opposite of what we wanted. It got us on the other side of the base. Of course, if you simply make a skip re-entry and go one orbit around, you will arrive at Cape Canaveral, but it's not that good. But anyway, we will see in another video how we can use the re-entry program a little bit better in order to arrive from the moon exactly where we want relative to the base that we want to land.
Yeah, again, this was this more simplified way of going from the moon to the Earth, like we did in the first set of videos. You know, you can go from the Earth to the moon, and there's an easier way to do it, but then you can also introduce the Delta V and map program to make a better trip out to the moon. Same thing here, coming back to the Earth from the Moon. This was the more simplified way of doing it. But in another example, Dimitri will help show how we can have much better targeting. But from my understanding, that's going to actually complicate things quite a bit.
Yes, a little bit, but once you get a hang of which variables you adjust and what that affects, it's the same as every other MFD. It simply takes a little bit of practice, and you end up with a much better flight, more efficient and faster.
Okay, well, that sounds real good. Well, we're well past 30 minutes on this video. We're coming up to actually just past 40 minutes, so go ahead and wrap it up here. But at the very least, this will help people get, make the round trip from the Earth to the Moon, and then also be able to come back to Earth from the Moon. So if you like the video, leave a comment down below, hit the like button, let Dimitri know that you appreciate all his help. I know I do, and I'll put a link to his YouTube channel in the description down below. Be sure to check out his YouTube channel as well, and I will see you in the next video.
Going to get us to Earth. So we can start by bringing up IMFD on the left.
Okay, let's do that. Let's bring up IMFD over here, and we have the default screen here, so we need to press the menu button, and we were bringing
and
up
we select the course program,
course,
and now we select the planet approach.
okay, so we'll go down to next till this is highlighted, then press the set button. That'll bring up the planet approach. This is pretty complicated looking stuff, so hopefully we can get a good explanation here of what we need to do.
Okay, the first thing we need to set up is a trajectory from the Moon to Earth. Now, the Moon is orbiting the Earth, so the reference planet over here, the central planet in our view, should be the Earth, and we select that by selecting reference and typing Earth.
Okay, could you maybe just expand on that a little bit? Why are we referencing the Earth if we're on the Moon? Is it just because the Moon's in orbit around the Earth?
Well, it's the same as TransX, where you have a major body.
Okay, welcome to another Orbiter 2010 video. And in this video, we are once again going to learn how to use IMFD. In the previous videos, we learned how to go from the Earth to the Moon. So now it's time to learn how to go the other way around, how to go from the Moon to the Earth. Now this scenario is one of the defaults that comes with Orbiter 2010. It's located in the Delta Glider folder. This is the Delta Glider landed at Brighton Beach. So if you load up this scenario, you should be able to follow along quite easily. I have Dimitri with me again to help us learn how to do this, because I am the IMFD newbie. I don't know much about it, so I have to have help for all these steps. So Dimitri, what do we need to do to use IMFD to get back to Earth?
Okay, hi everyone. Basically, I'm going to tell you the steps that we are going to do. We are going to use the planet approach program, so we have a trajectory to Earth. And once we have that, we're going to use the surface launch program in order to get into the correct orbit around the Moon, and then the orbit eject program to perform the actual burn that is
currently, of course, way out in space. And do we want like 65 kilometers for atmospheric reentry?
No, because right now the planet approach program is not very accurate from where we're standing right now. So you can set it around 500 kilometers, and it's going to get you to close to Earth. Anyway, we're going to make a course correction when we are inside Earth's sphere of influence.
Just out of curiosity, so IMFD, like all parts aren't equal, so it's just the map program that has that highly accurate model, whereas
Yes.
like these other programs don't quite have the same accuracy. Is that how that works?
Exactly.
Okay.
Exactly. This program is not that accurate, especially when you are already landed. If we were already on a trajectory to Earth, it would be slightly more accurate, the prediction that we get from here. But since we are right now, we are landed, and we have to go first into orbit and then eject to Earth, and after that, this is where that program takes over. It is latitude. It would be good to set up at least that much equatorial inclination. Otherwise, we're not going to have enough inclination to arrive at our base.
Okay, and just as a point of reference, if you don't know the latitude of the base, what you can do, bring up map MFD on the other side, reference the Earth, and then target the base you want. Let's use Cape Canaveral as our example. So if we target Cape Canaveral over here, then we have the latitude and longitude down here. And of course we want the latitude, which is 28.52 for Cape Canaveral. But you're saying that we wouldn't actually set the EQI to 28.52, rather we would maybe go a couple degrees higher.
Yeah, go to the next round numbers, something like 29 or even 30 degrees would be okay.
Okay, so we'll use the previous next and go down to the EQI and then hit set, and we'll just round it up to 30 degrees. Okay, so
now
then go
the
ahead.
next thing you set is the periapsis altitude.
Okay, so after setting the EQI, then we go down one and the PEA.
Body in the center and a minor body orbiting around it. And this is exactly what we're setting up over here. Now you can see, because we have the source, the ship right now, and not the moon, it tells us that we have an invalid source. So we have to change that, and we want the Earth at the center and the moon as the source.
Okay.
As the source of the trajectory, in a sense.
So when we selected the Earth as the reference, we were setting the major body, basically. And now we're setting the moon as the source. Now we have data that makes sense.
The Earth is right here at the center, and this blue and green line is the orbit of the moon. What we want to set up now is our approach to Earth. First thing that we want to set up is the equatorial inclination that we want to arrive at. Basically here we set up a number, a rounded number, relative to the latitude of our base. If we want to arrive at a base at 28 degrees